10.4 billion light years away, sitting at a point in cosmic history astronomers call cosmic noon, there's a structure so massive, so densely packed, and so improbably early that a team of astronomers ran the odds of it existing at all. The math came back at roughly 1 in 1,000 for the specific patch of sky they were looking at. It shouldn't have been there. And yet, when the James Webb Space Telescope turned its mirror toward it, the structure didn't just confirm it was real. It revealed something even more extreme sitting inside it. Gravity so concentrated in its core that it was bending and warping the light of galaxies sitting billions of years farther behind it. Everybody, this is the real story of XLSSC 122, a galaxy cluster that just set a new distance record for a genuinely rare phenomenon called strong gravitational lensing, and in doing so, handed cosmologists a structure that a growing number of researchers now say directly challenges the standard model of how the universe actually built itself. Let's start with what a galaxy cluster actually is, because the scale here matters enormously for understanding why this discovery is such a problem for existing theory. A single galaxy, like our own Milky Way, contains hundreds of billions of individual stars. A galaxy cluster is an entirely different order of magnitude, hundreds or even thousands of individual galaxies, each one containing its own hundreds of billions of stars, all bound together by their mutual gravity into a single, enormous, gravitationally linked structure. Galaxy clusters are the largest gravitationally bound objects known to exist anywhere in the universe, sitting at the very top of the cosmic hierarchy, above individual galaxies, above smaller galaxy groups, representing the endpoint of billions of years of matter slowly clumping together under the relentless pull of gravity. It's also worth understanding what astronomers mean by the specific term cosmic noon, since it's central to why XLSSC 122's era matters so much. Cosmic noon refers to a particular window in the universe's history, roughly 2 to 4 billion years after the Big Bang, when star formation across the universe as a whole was occurring at its most vigorous, intense rate ever recorded, considerably higher than the comparatively quiet, slower rate of star formation happening throughout the universe today. It's also the period when astronomers expect the first genuinely massive galaxy clusters to have still been in the earlier, more active stages of their assembly, growing and merging rapidly rather than having already settled into the calmer, more mature state clusters closer to our own present-day universe display. Catching a cluster in the act of finishing its formation during this specific window offers researchers a genuinely valuable snapshot, a chance to directly observe cluster assembly in progress, rather than simply studying the fully finished product billions of years later. XLSSC 122 sits squarely within that cosmic noon window at a measured redshift of 1.98, and that's precisely what makes its unusually mature, already dense characteristics so significant. It isn't simply an old settled cluster observed at an old settled time. It's a cluster caught in what should have been its formative, unfinished years, already displaying the kind of concentrated mass and structural maturity theory says shouldn't fully develop until considerably later in cosmic history. That framing helps explain exactly why Webb, and not any of the telescopes that came before it, was the instrument that finally cracked this particular case open. Webb's James Webb Space Telescope sits nearly 1 million miles from Earth, shielded from the sun's heat and light by a sunshield roughly the size of a tennis court, keeping its instruments cold enough to detect the faint, heavily redshifted infrared light traveling from objects billions of light years away. Its 6.5-meter primary mirror, built from 18 gold-coated hexagonal segments, gathers more than 2.5 times the light-collecting area of Hubble's mirror. Precisely the kind of sensitivity improvement needed to finally resolve the faint, strong lensing arcs that had eluded Hubble's own observations of this exact same cluster. That word, slowly, is doing an enormous amount of work in the standard model of cosmology, and it's exactly the word XLSSC 122 is putting under serious pressure. According to the widely accepted Lambda cold dark matter model, often shortened to Lambda CDM, the framework nearly all modern cosmology is built on, structure in the universe forms hierarchically. Small clumps of matter form first, shortly after the Big Bang, then gradually merge with neighboring clumps over vast stretches of time, growing steadily larger, generation after generation, over billions of years. Under that model, genuinely massive, dense, fully assembled galaxy clusters are expected to be a relatively late development in cosmic history, structures that needed the better part of the universe's entire lifespan to actually finish forming. Finding one that's already massive, already dense, and already gravitationally powerful enough to noticeably bend light, at a point when the universe was considerably younger than it is today, directly contradicts that gradual, patient timeline. It's worth understanding what the cold in Lambda CDM actually refers to, because it's central to why a discovery like XLSSC 122 matters so much to the underlying theory. The model assumes the universe is filled with a form of invisible matter, dark matter that interacts with ordinary matter and light almost exclusively through gravity, and that this dark matter moves relatively slowly or coldly compared to the speed of light, allowing it to clump together efficiently under its own gravitational pull. That slow, cold clumping behavior is precisely what's supposed to produce the gradual, step-by-step hierarchy of cosmic structure formation, small structures first, larger structures built up steadily afterward. Over a timeline, the model has been remarkably successful at predicting and matching to real observations across an enormous range of cosmic history. The lambda in the model's name refers to a separate component entirely, the cosmological constant, the term Einstein originally introduced into his own equations, now understood to represent the mysterious dark energy responsible for the universe's ongoing accelerating expansion. Together, cold dark matter and the cosmological constant form the two central pillars supporting the entire standard model of cosmology, a framework that has successfully explained an enormous range of observations, from the detailed structure of the cosmic microwave background radiation left over from the Big Bang itself, to the large-scale web-like distribution of galaxies we observe filling the universe today. A structure like XLSSC 122 doesn't threaten to topple that entire framework, but it does represent a genuine documented instance where the framework's specific predictions about timing and formation speed appear to be running up against real, directly measured data. XLSSC 122 first came to scientific attention back in 2014, spotted not by an optical telescope at all, but by the European Space Agency's XMM Newton spacecraft, an X-ray observatory designed to detect the extremely hot X-ray emitting gas that fills the space between galaxies in a genuine gravitationally bound cluster. That X-ray signature is actually one of the most reliable ways astronomers confirm a collection of galaxies really is a bound cluster, rather than simply a chance grouping of unrelated objects that happen to appear close together from Earth's vantage point, since only a genuinely deep, cluster-scale gravitational well is capable of heating surrounding gas to the extreme temperatures needed to produce that detectable X-ray glow. Follow-up observations using the Hubble Space Telescope helped astronomers pin down the cluster's distance more precisely, roughly 10.4 billion light-years away, and confirmed it already displayed unexpectedly mature features for an object that far back in cosmic time. But Hubble's data, as detailed as it was, showed no definitive evidence of the specific phenomenon that would eventually make this cluster genuinely extraordinary. If a real, current, actively debated discovery like this, the kind directly challenging the standard model cosmologists have relied on for decades, is exactly what you come here for. Subscribe now, because what changed once James Webb finally got involved is where the story becomes genuinely remarkable. Because in August 2024, a research team led by Kyle Finner, a staff scientist at IPAC, Caltech's dedicated science and data center for astrophysics and planetary science, pointed the James Webb Space Telescope's NIR-CAM instrument directly at XLSSC 122, originally intending to conduct a more routine kind of study called weak gravitational lensing analysis, a statistical technique used to measure a cluster's overall mass by looking at subtle aggregate distortions in the shapes of background galaxies. What the team actually found in that data went considerably further than what they'd set out to measure. Finner described the moment plainly, in words that capture exactly the kind of unscripted excitement real scientific discovery tends to produce. He said that when the team got those first images back from Webb, their reaction was immediate, essentially exclaiming, "Look at this, there's strong lensing coming from this cluster." It helps to understand gravitational lensing itself a bit more fully, because it's genuinely one of the most visually striking, directly observable confirmations of Einstein's general theory of relativity available anywhere in astronomy. Einstein's theory describes gravity not as a simple attractive force pulling objects toward each other in the way Isaac Newton originally conceived it, but as the literal curvature of space and time itself, warped by the presence of mass. A sufficiently massive object doesn't just pull on things around it. It actually bends the geometric path that light itself is forced to follow as it travels through the space near that mass. Astronomers first confirmed this effect during a total solar eclipse back in 1919, when astronomer Arthur Eddington measured a slight predicted shift in the apparent position of stars whose light passed close to the sun, exactly the deflection Einstein's newly published theory had calculated it should. Gravitational lensing around a galaxy cluster is that exact same physical principle, just scaled up dramatically, with an entire cluster's worth of mass, ordinary matter and invisible dark matter combined, doing to background starlight what our own sun's comparatively tiny mass did to the light of those distant stars back in 1919. Strong gravitational lensing is a considerably rarer and more dramatic phenomenon than the weak lensing effect the team had originally been hunting for. It happens specifically when a foreground mass is dense enough and concentrated enough to bend the light of background objects into distinct, visible arcs, rings, or even multiple duplicated images of the same distant galaxy, a direct visual consequence of that same relativistic curvature, just occurring at a scale and concentration extreme enough to produce genuinely dramatic, unmistakable distortions, rather than the far subtler statistical effect weak lensing measures across large numbers of background galaxies. When light from an extremely distant galaxy happens to pass close enough to an intervening mass concentration on its way to Earth, that curved space bends the light's path, and if the alignment and the foreground mass are significant enough, the result is exactly what Finner's team saw glowing in their JWST images, giant, unmistakable arcs of light curling around the cluster's center. Hubble simply hadn't been sensitive enough, or had the necessary resolution, to definitively capture that same signature. Finner summarized the technological leap directly, stating plainly that before Webb, this level of science simply wasn't possible in the early distant universe. Confirming and analyzing those arcs allowed Finner's team to do something considerably more precise than any previous study of this cluster had managed: directly measure the concentration and mass of matter sitting in the cluster's densest, innermost core, rather than relying on rougher statistical estimates. The results, published in the Astrophysical Journal letters, were striking. The team fit the cluster's inner 100 kiloparsecs, a considerable span given that a single kiloparsec equals roughly 3,260 light years, to a mathematical model called a Navarro-Frank-White profile, the standard framework cosmologists use to describe how mass, including invisible dark matter, is expected to be distributed within a gravitationally bound structure like this. The concentration value they measured came out to 6.3 plus or minus 0.5, an unusually high figure for a structure existing this early in cosmic history. The total mass packed into that same relatively small central region came out to roughly 6.5 times 10 to the 13th power in solar masses, meaning the equivalent of 65 trillion suns worth of material, concentrated into a comparatively compact core, at a point in the universe's history when structures this dense and this massive simply weren't supposed to have finished forming yet. The team's own published paper didn't shy away from stating the implications directly. They wrote that the high concentration of XLSSC 122 contributes to an emerging, broader picture, suggesting that massive structure formation in the early universe may proceed considerably more rapidly than standard cosmological models currently predict. That's not a minor caveat buried in a footnote. That's the central published conclusion of a peer-reviewed scientific paper, stating outright that this specific object doesn't comfortably fit the timeline the field's leading theoretical framework describes. Just how rare is a structure like this supposed to be under the standard model? The research team actually ran the numbers to find out, and the results underline exactly why this discovery generated so much attention within the cosmology community. Using the accepted statistical distribution for how galaxy clusters of various masses should be spread across cosmic history, and integrating across the specific redshift and mass ranges relevant to an object like XLSSC 122, the team calculated that within the specific survey area where this cluster was originally detected, the expected number of clusters this massive at this particular point in cosmic history was just 0.12, essentially predicting they shouldn't have found one at all within that patch of sky, let alone one dense enough to also produce strong gravitational lensing. Scaling that same statistical prediction up to the entire sky, the team estimated that roughly 193 clusters of at least XLSSC 122's mass should theoretically exist across the whole universe at this particular epoch. Finding even one, XLSSC 122 itself, places this cluster firmly in what researchers describe as the rare category of massive high redshift clusters that qualify as genuinely improbable detections, joining a small handful of similarly unlikely structures identified by other research teams in recent years, including objects previously cataloged as SPT-CL J2040-4451 and Sparky-S J-49-PLO56. The story didn't end with that first paper either. Once Finner's team had confirmed the strong lensing signature and measured the cluster's unusually concentrated core, two follow-up research teams, one led by Zachary Schofield and another by Hyungjin Ju, both working out of Yonsei University, used that same rich JWST dataset to dig even deeper into XLSSC 122's structure and history. Schofield's team examined the cluster using a complementary technique called weak lensing analysis, alongside data collected across multiple different wavelengths of light, and found direct evidence that XLSSC 122 is currently in the process of actively merging with at least one other massive structure, essentially catching this already improbable cluster in the middle of an ongoing violent growth spurt, adding even more mass to a structure that was already too large for its supposed age. Ju's team, meanwhile, focused specifically on something called intracluster light, the faint, diffuse glow produced by stars that have been gravitationally stripped away from their original host galaxies during the cluster's earlier violent merger history, and drift freely through the space between galaxies rather than remaining bound to any single one. Detecting and mapping that intracluster light at this particular point in cosmic history, right around 10 billion years ago, gave JWST's team what researchers describe as the earliest confirmed detection of this specific phenomenon ever recorded, direct evidence that XLSSC 122, despite existing this early in the universe's history, had already undergone enough violent merger activity to strip visible amounts of stellar material away from individual galaxies and scatter it throughout the wider cluster environment. JWST's team summarized their findings with a description that's become something of an informal tagline for the entire XLSSC 122 research program, describing the cluster as mature but still growing, a structure that already displays the hallmarks of an old evolved system, while simultaneously continuing to actively build itself through fresh mergers even now. Taken together, these three papers, Finner's original strong lensing discovery, Schofield's confirmation of an active merger, and JWST's detection of unexpectedly early intracluster light, paint a coherent, unsettling picture for cosmologists trying to defend the standard timeline of cosmic structure formation. This isn't a single anomalous measurement that might simply reflect an instrumental quirk or a statistical fluke. It's three independent lines of evidence, gathered from the same object using three different analytical techniques, all converging on the same basic conclusion that XLSSC 122 is simply too big, too dense, and too dynamically evolved for a structure that existed when the universe was roughly 10 billion years younger than it is today. It's worth being precise here about exactly what kind of challenge this actually represents, because it's easy for this sort of story to get oversimplified into something more dramatic than the underlying science actually supports. This isn't evidence that the Big Bang itself didn't happen, or that the broader expanding universe framework underlying modern cosmology is somehow fundamentally wrong. The overwhelming body of independent evidence supporting an expanding universe that began in a hot, dense state remains completely intact. What's genuinely being challenged is a more specific, more detailed piece of that broader framework, the standard hierarchical timeline describing exactly how quickly matter was able to clump together, merge, and assemble into massive, gravitationally dense structures like galaxy clusters in the universe's first several billion years. XLSSC 122 is part of a broader accumulating pattern of similar tension that Webb has been generating since its very first science observations, the same fundamental problem that's shown up repeatedly in Webb's discovery of unexpectedly massive, mature individual galaxies existing far earlier in cosmic history than standard models predicted they should. XLSSC 122 extends that same basic tension up to the scale of an entire galaxy cluster, arguably an even more difficult structure to explain away, given just how much more matter and how much more time standard theory assumes a cluster-scale object genuinely needs to fully assemble compared to a single galaxy. Astronomers currently have several competing explanations they're actively working through to try to resolve this tension, and it's worth being direct that none of them has achieved anything close to full consensus yet. Some researchers argue that the standard Lambda CDM model itself remains fundamentally sound, but that certain specific physical processes within it, how efficiently gas collapses into stars in the early universe, or precisely how dark matter behaves in clusters under gravity at these earliest cosmic epochs, may simply need meaningful refinement rather than wholesale replacement. Recent theoretical work published in 2026 by researchers at the University of California, Irvine, for example, has specifically argued that once you properly account for statistical selection effects, essentially the fact that surveys are naturally more likely to spot the rarest, most massive, most extreme examples of early structure first, combined with more careful accounting for measurement uncertainties across different studies, at least some of the apparent tension between Webb's early massive galaxy findings and standard cosmological predictions can be meaningfully reduced, even if not entirely eliminated. Other researchers take a more provocative position, suggesting that the accumulating weight of these discoveries, distant, unexpectedly massive individual galaxies, and now unexpectedly massive, dense galaxy clusters like XLSSC 122, may eventually point toward genuine physics beyond the standard model entirely, though this remains a minority position within the broader cosmology community, and it's a claim that would require considerably more accumulated evidence before gaining wider acceptance. What makes XLSSC 122 specifically valuable to researchers, beyond simply adding one more data point to this ongoing debate, is the unique scientific opportunity its strong lensing effect actually creates. Because the cluster's dense core is bending and magnifying the light of galaxies sitting even farther behind it in space and time, some estimated to be roughly 12 billion years in the past, researchers can use XLSSC 122 as a natural magnifying glass, studying background objects in a level of detail that would otherwise be far too faint and far too distant for Webb to resolve on its own, even with its considerable light-gathering power. That means this single, improbable structure isn't just valuable as a puzzle for cosmologists studying cluster formation, it's simultaneously functioning as a genuinely useful scientific tool, opening a clearer observational window into an even earlier, even more distant slice of the universe's history than astronomers could otherwise access directly. So here's where this genuinely leaves us. A structure so massive that standard models predicted researchers shouldn't have found even one example within the entire survey area where it turned up. A core so densely concentrated that it's actively bending and warping the light of galaxies from even deeper in cosmic history. Independent evidence confirming the cluster is still actively merging and growing, even as it already displays structural features. Astronomers associate with a considerably older, more evolved system. 3 separate peer-reviewed papers, 3 separate research teams, 3 independent analytical techniques, all converging on the same fundamentally uncomfortable conclusion for the standard timeline of cosmic structure formation. XLSSC 122 broke a distance record for strong gravitational lensing, but the more significant story sitting underneath that record is what its sheer, improbable mass and maturity implies about just how quickly the universe was capable of building its largest structures, considerably faster, it now appears, than the physics textbooks currently describe. If genuinely significant, actively contested discoveries like this, the kind forcing working cosmologists to publicly reconsider decades of established theory in real time, are what you come here for. Subscribe and turn on notifications, because Webb keeps finding structures like XLSSC 122 scattered throughout the early universe, and every single one adds more weight to a debate that is very much still unfolding right now.